Hello. Hello and welcome to this video. In this video, we will learn about how to delete a key from the B plus tree, which we have been discussing. So last two videos have been on insertion and the video prior to that was on uh, the theory of B plus tree. Now here is a fair piece of warning. When I started teaching data structure, I had shown the images how a node moves from one node to another. Now for this particular video or for the insertion of B plus tree, it would have been ideal if I could draw images for everything. But the problem is that it would require too much effort to actually draw the diagram of every possible case. And it is not a beginner data structure, it is an advanced data structure. So some effort has to come from your side. So to understand what I'm going to tell you, what you need to do is you go and insert a lot of nodes, not only 7 nodes, because 7 nodes will be basically put inside 2 nodes with our order 3. If you remember, our order was 3. So what you need to do is you need to insert a lot more nodes, probably 30 or 40 nodes, or other keys, 30, 40 keys, so that you get somewhat a larger B plus tree. Once you have that, you can follow this piece of code, which I'm going to show you, and use pen and paper to execute every line that how it works. That will be the secret of understanding how this is going to work. It is not a simple linked list or a binary tree that you can simply understand just like that by looking at the code and understanding it. It is quite complicated. I think it is the most complicated piece of code going to be which I have covered till now. Insertion was relatively easier. So uh, probably sometime later I will draw the diagrams and animations. It will require a lot of effort from my side, but I'll see if I can do that. But here I will put that onus of the hard work on you. I'm sorry about that. But let's get started on how we are going to delete a key. So the first function is delete key. What it does is it takes the root here and it calls a delete key helper with root and key. Now we look at delete key helper, what it does. So what it does is it tries to find the key. Okay. Now we look at find key. So what it does is it takes the node and the key and it iterates and goes on increasing the index till the index is less than the n value of node, that is how many keys it have, or the key is greater than node keys at that index. So from this you can observe that if the node is not found, if the key is not found on this node, possibly what can happen is that this index can become equal to node n. Okay. The second thing which can happen is that key can become greater than node keys. Okay. In that case, index will be less than node n, and we return this index. Now, once we have this index, there are two possible things which can happen, or rather several cases which will happen. So one of the cases which I already talked about is that index is less than n and we have got the key on the node. If that is the case, then we have two possible cases. One is that node is a leaf node. If it's a leaf node, we simply remove the index from the node. So we call remove from leaf. So how do we really remove from leaf is that we have the node, we have the index. Okay. So we iterate over the index, and what we do is from the ith position of the key, we put it on I minus 1 and we remove the n by 1. That is how we remove from the leaf. So that is quite simple to understand if you have understood how the index insertion works. Now, if the node is not leaf node, what we do is like a binary tree, we find the predecessor. Okay, and we put the predecessor in the at the index position of the keys, and then we call delete key helper again, where we pass the node children index and the predecessor. Let's see how do we get predecessor. So suppose we have a node, we have an index, and we want to find the predecessor. So we mark the child which is at index position as the current node, and till this is not a leaf node, that is uh, while the leaf is false, what we do is we put this current as children current n. So we take the n value of current and we find that child and we put that in current. And at the end, we return current keys current n minus 1. So that's how we find the predecessor. Okay. So that is quite similar to what we do in binary tree. Now, once we have the predecessor, we call the delete key helper. Now, as I said, what can happen is that index can become equal to n, okay, and the key may not match. So in that case, we check if the node is leaf node. If it's a leaf node, then obviously the key is not found in the V plus tree. Now, if the index is equal to node n, which will be true in this case, it will be the last child. And then we check if the child or the child at index position and the n value of that is less than node t, then we fill the node. Okay. Now, if the last child has been merged, it must have merged with the previous child. So we need to recursively delete the key from the previous child. So in this case, what will happen is last child will become true and index will be greater than node n. Okay, but here we found the equality, but so we may not enter this, we may enter this. So it depends what index we got here. Okay, it is not necessarily that it will be equal to node n. It can return before that also. Okay, so these two cases, what we do is we again use delete key helper and we send appropriate index of the child with the key. So that was delete key helper. Now, here we have not seen, where is the thing? Fill. Okay, we have not gone and seen what fill does. We will see that in a bit. We go back to delete key. Now, suppose root has no key left and it has a child. Make its first child the new root. So now in this case, what can happen is the root n may become 0 and root may not be a leaf node. In that case, we make the root node the first child of the root. So, and after that, we free the root. Okay, now we go and look at fill function. Now we are going to go in seriously complicated zone very soon. Okay, by now I've lost it. All right, I don't know what will happen anymore. Okay, so there are three cases which can come here. If index is not equal to 0 and the child at position index minus 1 and n of that is greater than node t, then you borrow from previous. And if index is not equal to node n and the child at index plus 1 position and n of that is greater than equal to node t, then you borrow from next. So see how complicated this has become. You will have to have pen and paper and then you need to draw and understand that what is going to happen. Now if these two cases are not satisfied, then what we do is if index is not equal to node n, then we merge node at position index. Else we merge node with index minus 1. That is the argument we are passing to merge. Now we have three complicated functions: borrow from previous, borrow from next, and merge. So if you have seen my first video, the animation which I have shown in the first video of B plus tree, then you will see that these things actually happen, that the merger and split and those things happen when you insert and delete nodes. So first we will see how do you borrow from previous. Okay. So you may want to read the comments here, that what it does. It's a function to borrow a key from the previous child and move it to the indexed child. Okay. So what we do is we create a node, we take a node child which is at position index, and then we have the previous child that is at index -1. So we call that sibling. We could call it previous, that would be a better name. Now the first thing which we do is we iterate on the child, and what we do is we go till n-1 and I greater than equal to 0, and we go on decreasing I. So we start with the rightmost index and we go on. What we do is we shift the keys. Okay. So here you see what will happen. It will be child n-1 to begin with, and it will go at child n. So what we are saying is that keys are being shifted right. Okay. So that's what we call it one step ahead. So once we have shifted all the keys, there will be one position which will become open. That is where we will put the key which we get from the previous child. Now, if the child is not a leaf, move its child pointers one step ahead. So if the child is not leaf, we move the child pointers one step ahead, just like we did with keys. Now, what we do is we the first key which the position is vacant, we fill that with node keys index -1. Okay. Once we have that, what we do is we move the previous nodes or the siblings last child as child's first child. Okay. We have shifted keys here. We have made the 0th key, which position was become the position became vacant, but we also shifted children. But here the 0th position has become empty, which we have not filled. So we'll fill that here. So we take the siblings children and we take the last of those and we put it at the children 0. So from previous we are borrowing the child here. Now we move the key from sibling to the parent. Remember that the key which we moved here, that has to be filled. So we take that from the previous and we move it to the node. So once we have done that, we increment the n count of child and decrease the previous node. So if you can imagine the b plus tree in your head, it will be quite easy. And it's not really complicated. I hope that I have explained properly. And that's how the borrow from previous works. Now we do borrow from the next. So it will be quite similar to what we have done. So again, we have a child and we have a sibling. So as you can guess, the index of the sibling will be one more than the index of the child. Once we have that, what we do simply is we move the key of the node at position index to nth position of the child for the keys array. Now if child is a leaf, what we do is we take the sibling's first child and move it n+1 position. Okay, that is, we are borrowing the child from sibling. We borrow one child. Once we have that, what we do is we take the key from sibling and put it at the node keys index, because that's what we have moved here. So the keys are managed here and child we have managed here, but there is still one child is remaining, okay, which we'll see. Now once we have done that, we move all the keys in sibling one step behind. So this is kind of reverse of what we did here. Okay, so once we have done that, the sibling keys, okay, one position which will be empty, that is sibling key 0 position, that will be filled, and we will eventually decrease the n of sibling, so that will make sense. Now, if sibling is not a leaf, move its child pointers one step behind. Now, since the keys are moved, the children have to be moved one step behind. So that's how you borrow from the next. So again, if you can imagine, it will make sense. If you can't imagine, then you use pen and paper and do the uh, movement by hand, and you'll see how this works out. So it's not terribly difficult till now. Uh, but if you don't understand b plus 3, or if you have imagination problem, then it will be difficult. So in general, it can be quite difficult to understand just like that. You need to be attuned to what b plus 3 is. If you don't understand the structure of b plus 3 or how insertion works, there is no way you are going to understand what I just talked about. So make sure you watch the first two videos and you understand those. Now we come to the last function, that is the merger of two nodes. Okay. So this function merges the index child of node with index plus 1th child of node. So we take child, which is at indexed position, and we take sibling, which is at index plus 1th position. So what we do is we pull a key from the current node and insert it at t minus 1th position of the child. So at the child end position, we put the one of the keys. Now if child is not a leaf node, we move its child pointers one step ahead. Okay. So what we do is we take the children 0 and we move it to child n plus 1. Now we copy the keys from siblings to child. So from the sibling keys, we move it to children. Okay. Now, if child is not a leaf, copy the children pointers as well. We have moved the keys and then we move the children here. Okay. Now, once we have done all that, you see, sibling keys are now part of child keys and sibling children are part of child key. Now remember that we moved this key, okay, from the index position. So we need to fill that. Okay. So what we do is we move all the keys after index in the current node one step before so as to fill up the gap created by moving keys index to child. So we do that in this loop. Once we have done that, we move the child pointer from index plus 1th position in the current node one step before. So that's what we have done here. Once we have done that, we update the children n. So now the children n would be sibling n plus 1. And node n will be decreased once because one node sibling is going to go away. Okay, once the sibling goes away by calling free. So this is the entire process of deletion. Okay, now as you can see, when you actually delete a node, this fill may not come in picture. Okay, it may not come in picture, it may not, you don't know. So similarly, even if fill comes in picture, what can happen is borrow from previous may come in picture, borrow from next come in picture, or these merges can come in picture. So you see there's quite a bit of branching. That means there are lots of possibilities of what can happen depending on the current positions of nodes and keys in the B plus tree. So it is non-trivial to exemplify this. That is why I said in the beginning that you need to insert a lot of nodes here. So for example, we have order is equal to 3 and we put in how many children? 2 into t key children with 2 into t minus 1 keys per node, that is 5 keys per node. So suppose you have 6 children, and since we know that all the data is in the leaf nodes, so suppose you have 4 nodes as leaf nodes, so 4, 6, 24, you will need to insert at least 24 elements to get a picture of what is going on here. And that way you will be able to traverse all the paths in the delete key operation. Okay. So I promise that I will make the animation, not really animation, I'll make the images for this, okay? It will be difficult, it will take me good 4 or 5 days to create all the images, for sure, I know. And I will show you this entire code base, how this works, okay? But I'm not sure when I will get the time to create all the animation for this, but I promise that someday I will make it. It depends when I get the time of 4 or 5 days to do this, because as you know, from my other videos, I'm busy writing the book. So as soon as I get the time, I'll make all the images explaining that what is happening in all this code base. Okay. So please be patient, and till that time, my advice would be that you take pen and paper, insert these nodes, or you use a debugger to insert the nodes along with the diagram on the pen and paper, and then go through each line by line code in the debugger, and at the same time you adjust your diagrams with pen and paper to really understand how the B plus tree works. So with this, we come to the end of B plus tree, and in the next video, we will touch upon segment trees, because segment trees are quite useful for competitive programming. There are lots of problems where you need segment trees, and they have quite interesting properties on how to deal with certain kind of problems. So thanks a lot for watching this video, and I appreciate your patience, because although I have explained the code, the problem is that you may not have understood that what I was talking about. So if you have not understood, then you proceed with the suggestion which I have given you. And if you do not understand even then, leave me a comment and I will try to uh, expedite the process of making the diagrams, and I promise the diagrams will come sooner than what you have expected. I think I will create diagrams for all the discussions where I have not done the diagrams, like AVL tree or red black tree or even splay tree. So whatever we have discussed, I will make the diagrams and I'll go through the code again, going through line by line. So those will be quite long videos. So please wait for that. And I appreciate your patience for that wait. So thanks a lot for watching the video. I'll see you in the next one. Happy programming.